Good morning, guys. Okay, who is really talking? Okay, Jan, if you may mute yourself, it would be nice, but it's okay. I muted you. All right, that is disturbance. Okay, now what we are going to do is we are going to start chapter 17. By the way, tomorrow we don't have a Zoom session because of development today. So don't show up, okay?
Thanks for letting us know.
All right. Yeah, we will have once a quarter developmental day, that is really going to cancel the class. All right, we'll start chapter 17, which is parameterization and vector field. That's we are going to focus on. And parameterization, you guys are familiar with, but it is really instrumental for us. And we are going to discuss it again. And it is important aspect when we are dealing with vector valued function. As you know, the vector valued function, when it is written in the component form, actually the x component, the y component, and the z component are parametric, set of parametric equations. Okay, parametric equations are useful in actually describing motion along a curve. And this kind of motion, we call it whether it is curvilinear or rectilinear motion, motion along a curve or motion along a straight path. So the parametric equation will have the form x as a function of t, y as a function of t, and z as a function of t. Also, if we have three actually dimension, if it is two dimension, drop z. So for example, find the parametric equation for the curve x is equal to 3 over 4 y squared. Well, there are so many ways of doing this one, between -4 and 4 in two dimension. Well, one of the possible parameter, if I make, for example, x is equal to 3t squared, then y is equal to what? Well, y is equal to 2t. Then if you put here, actually, t equals y over 2. And if you plug it here, it will be 3 over 2, 3 over 4 y squared. So we can find also the parametric equation of a circle of radius r. You guys are familiar with. It is x is equal to r cosine of t, y is equal to r sine of t, and why I said familiar with, because we studied polar coordinate. And find the parametric equation corresponding to the equation equals y equals x squared minus 4. Well, you can have infinitely many ways of representing parametrically a single function, as you know. And that is why this flexibility actually allows us to use it in calculus more frequently. So, for example, if I let x is equal to t, then the parametric equations are x equals x of t and y is equal to t squared minus 4, from negative infinity to positive infinity. Alternatively, I can make x is equal to t cubed. If I make it t cubed, what will happen? Y will be t to the 6th power minus 4, and the same thing. So if the parameter t represents time, then the parametric equation x of t and y of t specify how the x and y coordinates of a moving object varies with time. This motion referred to us as curvilinear motion, and the parametric equation specifies not only just where the object is, but also at what time. So that is actually what the important aspects of this. So why not I give you these problems and try to draw the parametric curve A, B, and C. X is equal to cosine of t, y is equal to 4 sine square root of t between 0 and pi. Let us start with that one and then we'll move on.
I have a quick question.
Yes, sir.
Yeah, we'll be doing Jacobians.
Yeah, we will work. Why?
Yeah, because
huh?
it was chapter 16.7.
Yeah,
so
we'll come back and work with Jacobian. I will show you 16.7, okay?
sweet, thank you.
All right. That's good, actually. Change of variable and it is really important, but what I'm going to do is when I do actually line integral, it will help me. We'll come back. And actually, thank you for reminding me. I will let everybody to wait for section 6.7 to do their homework, okay? The textbook. Thank you. Okay, first of all, let us really eliminate the parameter. What we can do is we have x is equal to cosine of t and y equals 4 sine square root of t. And this one, it is given between 0 . So how can I really do this one? Well, if I square the first one, x squared is equal to cosine square root of t. And that means, and here y squared over, and if I add them together, what do I have? X squared plus y squared over 4 equals 1. Then this is really going to be part of what? I'm sorry. This is x squared, this is y. I'm sorry, y. Y over 4. And when you are adding, you will get this. So what we have is equal y over 4 is equal to 1 minus x squared, and y is equal to 4 into 1 minus x squared, and it is going to be a portion of the parabola. If you want, you can really make the table and draw the parabola. Yeah, it starts, for example, when t is 0, cosine of 0 is 1, sine of 0 is 0. So at 1, 0 it will start. And if we put pi, again, cosine of pi is -1 and the sine of pi is 0. So from 0, 1, 0, 2 to 0, 1, it is really going. It's a portion of the parabola. And as you know, the parabola opens downward, and the vertex is going to be at 0, 4, and that's it. So if you want to draw it, it will start from 1, 0, and here it will come to 4, 0, and it will come to -1, 0, and the motion is this, and it will be a counterclockwise direction. And that's it. Is it clear, guys? If you have any question, just ask me and I will explain. Otherwise, that's it. You can prepare table as well. You can prepare table of values, and in this case, you have one input and two outputs, t, x, and y. And then you can really pick this common point. For example, 0, pi over 6, pi over 4, pi over 3, pi over 2, and so on. And you get the first half, and the second half will be explained, and just pi. And you plug it into the equation, as I said. For example, when t is 0, cosine of 0 is 1, sine of 0 is 0. And when it is pi over 6, you will do the same thing. The cosine of pi over 6 is a radical of 3 over 2. And sine of pi over 6 is 1/2, and that is 2. And so on and so forth. You can prepare table, but that is really boring. You can really handle it this way. All right. If that is the case, now I'm going to give you this question. Find the parametric equation that traced out the ellipse, which is given by x squared over 4 plus y squared equals 1, where the parameter t is time in second, and a, the motion around the ellipse is counterclockwise, begins at the point 2, 0, and require first for a complete revolution, requires 1 second for complete revolution. And the second one is the motion around the ellipse is clockwise, begins at the point 0, 1, and requires 2 seconds for complete revolution. Try to come up with this parametric equation, because we need to know all this. So you have x squared over 4 y plus y squared equals 1. And t is time in second. And the first one, you start at the point 2, 0, and requires 1 second to complete the revolution. And b, the motion around the ellipse is clockwise and begins at the point 0, 1, and requires actually. Okay. The internet is unstable. Are you okay, guys? Can you hear me well? Okay. Okay, the video is not really good. What about now?
I can't really read that. I did hear what you said for the first part of the problem, and I wrote that down. So.
Okay. Sorry, I will write it. Let me write the equation. X squared over 4 plus y squared is equal to 1. And the starting point first 2, 0. And this is counterclockwise. Counterclockwise. And in 1 second. And B, again, x squared over 4 plus y squared equals 1. Starts at the point 0, 1. And clockwise, uh, 2 seconds to complete one revolution. Okay, well, let us do that. This. The first one, when t is equal to 0, then what is it? X is equal to 2 and y is equal to 0. So the x value is going to be actually a number. Therefore, x of t, what I have to do is, as you know, I can write 2 times cosine of omega t. And the y value, simply let me write it at sine of omega t, because this is angular velocity, or what we call it actually the the frequency of the movement. It is going to be determined, and we'll work that. So for the motion to be counterclockwise, as t increases from 0, the value of x must decrease and the y value must increase. This requires what? Omega has to be greater than 0. So if omega is greater than 0, then x is equal to cosine of omega t is decreasing when t is greater than 0, near 0, and y sine is increasing t 0. So one revolution takes 1 second. So one revolution is, the period for one revolution is 2 pi divided by omega, angular speed, then it equals 1. Then from here, I have to solve for omega. So what do I have? Omega is equal to 2 pi. Therefore, my equation is going to be x of t is equal to 2 times cosine of 2 pi t, and y equals y of t sine of 2 pi t. Is it clear, the argument? So the time is 1 second. And that is really what we need to do. Okay, by similar argument, can you try to make actually for the second one? It is within 2 seconds, and it has to be so to make it actually now clockwise direction, what will be the x value? What will be the y value? Anyone? X of t equals what? Shall I make it sine or cosine? You already learned this one in your trigonometric class. Well, we make it sine, and you will see it actually, sine of omega t. And y of t is equal to cosine of omega t. And remember, when you were talking about the spring motion, where it's going to be starting? Is it in the actually equilibrium position? If it is equilibrium position at time t0, it is 0. Therefore, for the vertical motion, what shall I do? You will say, or the pendulum, which is really moving, the x coordinate and the y coordinate. The same argument that we make is going to be done here. So now we have to make omega greater than 0 as this one. Since one revolution takes 2 seconds, one revolution, the time is 2 seconds. Therefore, 2 pi over omega is equal to 2. Then from here, what I have is 2 pi is equal to 2 omega, and omega equals pi. Therefore, x of t is equal to 2 times sine of pi t, and y of t is equal to cosine of pi t. By the way, we might be required, and by the way, t is changing between 0 and 2. And these are actually, that is what you need to remember. So parameterization is really very important, and we learn it so many times. And I want to really practice. Okay, I will give you one more practice for 3-dimension, and then parameterization. It is a lot. You have done it, and I'm not going to waste a lot of time. Instead, actually, I will go to some parametric equation of a line and so on. So, find the parametric equation for a particle that starts at 0 point start, 0, 3, 0, and moves around a circle counterclockwise on the YZ plane. So if you try to draw it actually the object and like this, then what is really happening is on the YZ plane, it is rotating counterclockwise. So what is the parametric equation for that?
So it starts at 0, 3, 0. Isn't that on the y-axis? How? And it rotates in the YZ plane.
Okay. So what happens is you have the x the x value is 0. Okay. Hold on. Start at the point, actually what? At 0, 3, x is 0, the x value is 0, the y value is 3, and then actually the z value is also 0, and then it is really rotating or move around what? A circle counterclockwise on the YZ plane. So it starts here and move like this. By the way, my picture sucks. Okay? Is that your question? This is a YZ plane on the parallel to the YZ plane. Actually, it is not on the YZ plane. Exactly parallel to that, and it is rotating. The starting point is what? Hold on. You have here the point, and then it is really moving like this. This is the YZ plane, yes? The X plane is far on this plane, moving like this one. Okay?
I don't think I'm following you. So is the circle in the YZ plane, is that centered at the origin or?
It starts, not center.
Yeah.
Okay, you have this YZ plane, Z, and here Y. All right, the X is 0. Then now the Z value is 0. At 3 it starts here, yes? Okay. Can you see it here?
Yeah.
This is 1, 2, 3. And it is moving counterclockwise on this plane. Like this. And assume that the x-axis is really coming and it is not on there. Okay?
So the circle that it describes the path of motion, is that centered at the, okay, that was what I was trying to ask.
It is not the center, the starting point. We are not talking about the center, okay? That starts at 3, 0, at 0, 3, 0, and move in counterclockwise. So, on the YZ plane, what is the x value equals?
0.
0. So x is equal to 0. So we get that. And now we have to come up with y, because it is really creating a circle. Y equals a function of some variable, and z also a function of some parameter variable. That's what we are going to do. For example, if I make omega 1, what will happen? To make it the counterclockwise, the horizontal plane has to be the cosine value. Therefore, this is going to be 3 cosine of t. And because it is a circle, the coefficient here has to be also the same, yes? So the z value also becomes 3, and that is sine of t. And your parametric equation is going to be this. That's it. X is equal to 0. Y is equal to 3 cosine of t. Z is equal to 3 sine of t. All right. These are really the parameters that we are going to follow. Okay. Now, how about parametric equation of a line through the point? Equation of a line through the point x sub 0, y sub 0, and z sub 0. And parallel to the vector Can you unmute yourself, somebody who is actually struggling? I know, 0 to 2. Okay. All right. And I will give you the parallel vector. Actually, sorry, I get distracted. So the parametric equation for the line through the point parallel to the vector, this is going to be given by x is equal to x sub 0 plus 18, y is equal to y sub 0 plus bt, and z equals z sub 0 plus ct. You might really remember this derivation earlier. For example, if you have actually a line in 3D and it has a point which has x sub 0, y sub 0, and z sub 0, and a direction vector which has a component, let's say a, b, c, and you will pick a point here, coordinate x, y, and z. Then this one is going to be your position vector, r sub 0, and this is your position vector, which is r. And this has a component also, x sub 0, y sub 0, z sub 0. And now let us say this is point P and this is point Q. Now this vector V is parallel to PQ. If V is parallel to PQ, what can we say? Well, what we can say is actually PQ equals the scalar multiple T times V is going to be the two vectors. If two vectors are parallel, one is a scalar multiple of the other one. That is what we do. Then now what do we really come up with? This vector R is actually this vector R sub 0 plus vector PQ. Vector R equals R sub 0 plus vector PQ. And that is R equals R sub 0. And PQ, we can be replaced by T times V. And that is what? If you really write the component of R, it is X, Y, and Z equals the component of R sub 0, X sub 0, Y sub 0, Z sub 0, and plus T times the component of V is A, B, and C. And as you see, this vector equals the sum of these two vectors. And if two vectors are equal, each components are equal. That means X is equal to X sub 0 plus TA. That is why Y equals Y sub 0 plus TB. And Z equals Z sub 0 plus TC. That is what we have the parametric equation of a line. All right. If that is the case, I'm going to give you, by the way, is it clear? This derivation, do you remember doing this? Yes? Yes, all right. If you really remember this one, and we have done it, and now what I'm going to do is find a parameter and a vector equation for the line through the point. Okay, the starting point I'll give you 1, 2, negative 1. And the destination point, let me give you 4, 3, 2. It doesn't matter actually. You can pick either way and so on. So I want to give me the line containing equation of the line containing these 2 points, both the vector and the parametric. Okay, so what we are going to do is really draw, for example, randomly. It doesn't have to be necessarily perfect. Okay, let us say this is my point, 1, 2, -1 in this line, and the other line is here, 4, 3, -2. And now I want to come up with the parametric equation of this line. Well, in the first place, I need to find V, this one, PQ. Let us call this one P and Q. And actually, it can be a scalar multiple of V. Then now, vector PQ equals 4 minus 1 and 3 minus 2, and then -2 plus 1. And that will give me 3, 1, -1. Okay, I have this actually direction vector. If I get actually that, then what can I do? Well, you remember we come up x is equal to x sub 0 plus at, y equals y sub 0 plus bt, and z equals z sub 0 plus ct. We can write it, assuming that this is a, b, and c. And our x sub 0, y sub 0, z sub 0, let us write this one. Then as a result, 1 plus 3t, and the second one is 2 plus t, and the last one, the z value, you can write it as -1 minus -t. And if you want to write it in a vector form, r equals r sub 0 plus bt. And r is x, y, z. And r sub 0, which is 1, 2, -1, and plus t times those components 3, 1, -1. Either this or these are representing the same line. So from here, what I'm going to really lead you is we can write the parametric equation x is equal to x of t, y equals g of t, and z equals h of t as a single vector equation, just like we did here. And this is of this form. R of t is equal to f of t I plus g of t j plus h of t k. And this is called actually parameterization. What we are doing is when we are writing this equation, we call it, this is parameterization. So parameterization is really giving a vector equation for the curve by introducing one single parameter, which is t. And that is really what we need. So the circular motion in a plane x is equal to t, y is equal to sine of t can be written, for example, a circular motion this is parameterization of a circle, or for that matter, helix. You can really parameterize it as cosine of t, sine of t, and t. By the way, as linear combination of I and j, or in a component form, you can write that as well. So you can write it like that as well. Okay, now what I'm going to ask you is, this is the example. This will be the last example for today, and we'll continue tomorrow, actually. For example, when things are going, are they intersecting, or they pass, or they do not intersect, or collide? That is kind of problem we'll see. Now, what I'm going to ask you to do is use vectors This is exactly from your textbook. I am copying it. Use vectors to give a parameterization for the circle of radius 1/2 centered at the point -1, 2. Okay, so what we are going to do is use a vector to give a parameterization for the circle of radius 1/2 centered at the point 1, 2. Well, let us start actually with equation of a circle. Equation of a circle centered at the origin having radius 1. Let me start with the simplest one. If I have a circle of radius 1 centered at the origin, its vector equation is going to be what? Let me call it R of 1. It will be cosine of t and sine of t, because the radius is really 1. All right, and that is from 0 up to 2 pi in order to get this complete revolution. Okay, a point 1/2 is the position. Point, actually, -1 and 2 will have a position vector. Let me call it R sub 0. What will be? -1 and 2. That is a component. And now what I'm going to do is, if I try to really locate this, okay, I will have the position, let's say -1, 2, somewhere here. And I call it R sub 0, and that is it. This is -1, and this is really 2. And now I'm going to really move this circle and bring it actually from this center and bring it over here. And this circle is going to be really 1/2 of R1. The radius 1, it is 1/2. And now I want to get this vector R, because this vector R is when the circle is rotating like this. So if I add these two, I will have that vector. So vector R, let me write it here, equals R sub 0 plus 1/2 of R1. Well, R sub 0 is actually 1, -1, 2, and plus 1/2, and that is R1 is cosine of t, sine of t. Well, I ran out of space. Are you following what I am trying to show you? Look, this R is really changing. When it is here, it is really pointing this way. When it is over here, also, it is the same as this R sub 0, and this is 1/2 R times t. And if it is over here also, it's the same thing. So it is the equation is going to be R equals R sub 0 plus 1/2 R1, and R sub 0, as I said, -1 and 2, and 1/2 of cosine of t and sine of t. Well, this has a component xy. So the x component is going to be -1/2 plus 1/2 cosine of t. And the y component is going to be 2 times 2 plus 1/2 cosine of t. So this is really the parametric equation of the circle centered at the point -1, 2, and having radius of 2. So this is how we do parameterization, and we might be required actually to do a lot on this. Thank you for your attention. I will see you Wednesday, and we will continue this section as well. And by the way, On the textbook, it is not the Jacobian on the lecture notes. If it is really included, don't do it now because when we are doing line integral, surface integral, we need to really learn parameterization. So the minute I finish chapter 17, we will learn the Jacobian. Okay? Yes, sir. Yeah. We don't meet tomorrow. We meet Thursday and Friday. Okay? And you will have a quiz starting 3 p.m. on Friday as well. I put it on the announcement. You might see it. Okay.
Could you allow late passes on WAMAP?
Yeah.
Can you add late passes?
What?
Late passes on WAMAP for the WAMAP homework, like the past homework?
Didn't I give you late pass for everybody?
No.
Anyone? You don't have any late pass, guys?
No.
Okay. We'll check it, okay? If I may, I will give you a late pass. If you overused it, that is your problem. Have you ever used it before?
No.
Okay. I will check it, okay?
Okay, thank you.
All right.
See you Thursday.
All right. See you Thursday.
Thank you.